Hello students, we are dealing with the unit of inverse Laplace transform, and so far we have studied 5 different methods to find inverse Laplace transform of the given function of s. The methods are use of standard results, use of shifting theorem, use of method of partial fraction, use of differentiation of f bar of s, use of integration of f of t. Now the next is very similar method and simple method, that is use of differentiation of f of t. We have seen the use of differentiation of f bar of s method. Now we are going to see the new method, use of differentiation of f of t. This is also one of the useful methods to find the inverse Laplace transform, but very rarely examples based on this point are asked in university exam. But this method can be useful to find inverse LT using another methods, that is convolution theorem. So we are going to study now the method of use of differentiation of f of t to find inverse Laplace transform. By Laplace transform of derivatives, we have, if L of f of t is equal to f bar of s, then L of d by dt of f of t, or you may call this as L of f dash of t, is equal to minus f of 0 plus s into f bar of s. So if f of 0 is equal to 0, then L of f dash of t or L of d by dt of f of t becomes s into f bar of s. Now taking inverse Laplace transform on both the sides, we get d by dt of f of t is equal to L inverse of s into f bar of s. So if some function f of s or f bar of s is multiplied by some power of s, then we can apply this method where we are going to find inverse LT of f bar of s, and then we are going to take differentiation of that f of t. So if L inverse of f bar of s equal to f of t, then L inverse of s into f bar of s equal to d by dt of f of t. Obviously, if f bar of s is multiplied by s square, we have to take second order derivative of this f of t. If it is multiplied by s cube, we have to take derivative of f of t 3 times. So the power of multiplier s decides the number of derivatives we have to take to get the final answer. Now we will see the procedure in short. First step, identify f bar of s, that is the term other than s or s raised to n factor whose inverse LT can be obtained using the previously studied methods. So you have to identify or you have to consider f bar of s very carefully. Now you have to find its inverse Laplace transform, which you are going to call as f of t. Then to find inverse LT of s into f bar of s, you have to take derivative of f of t. If it is to find inverse LT of s square f bar of s, then you have to take the derivative of f of t 2 times. Now we will see one example. Question will be same, find inverse LT of. Now here the first example is s square upon s plus 1 bracket cube. So this can be written as s square into 1 upon s plus 1 bracket cube. Now if I consider this as f bar of s, then I can find its inverse LT using the shifting theorem method. So this f bar of s is correct to apply the method of use of differentiation of f of t. Now we will see the solution step by step. So as per the discussion just now we have regarding f bar of s, here f bar of s is 1 upon s plus 1 bracket cube. Take its inverse Laplace transform. So L inverse of f bar of s is equal to L inverse of 1 upon s plus 1 bracket cube. So applying use of shifting theorem method, we can write it as e raised to minus t into L inverse of 1 upon s cube. Now using the standard results, we can find L inverse of 1 upon s cube, and it is equal to t square by 2 factorial. 2 factorial is same as 2. So final answer is e raised to minus t into t square upon 2. So this is our f of t. Now we have to find the inverse LT of the given function. So you have to write here the result we are going to use, but we know that L inverse of f bar of s is equal to f of t, then L inverse of s into f bar of s is equal to d by dt f of t. Now here in the given example, this function f bar of s is multiplied by s square. So this degree 2 indicates that we have to take d by dt 2 times. So we are going to find derivative of this function f of t 2 times. So using this result, we will find the derivative step by step. First we will consider L inverse of single s and not s square. So remember, note down this one. This is, we are finding L inverse of s upon s plus 1 bracket cube and not s square upon s plus 1 bracket cube. So using this result, you have to find derivative of f of t, that is e raised to minus t into t square by 2. Here there is a multiplication of or product of two functions of t. So obviously we have to use multiplication or product rule of derivative to find this answer. So L inverse of s upon s plus 1 bracket cube equal to d by dt e raised to minus t into t square by 2. Here 1 by 2 is taken as constant multiplier out of the derivative sign. Now applying d by dx of u into v rule, we get this answer. So here derivative of e raised to minus t, that is e raised to minus t upon minus 1. So it becomes minus e raised to minus t, v function t square as it is, plus derivative of v, that is derivative of t square, it is 2t, and u function as it is. On simplification and writing the positive term first, we get this answer 1 by 2. T e raised to minus t is a common factor in both the terms of this curly bracket. So 1 by 2 t e raised to minus t into bracket the uncommon terms 2 minus t. Now this is not the final answer, as we have to find L inverse of s square upon s plus 1 bracket cube. So we have to take one more time derivative of this latest function of t. Therefore L inverse of s square upon s plus 1 bracket cube is equal to d by dt of the latest function of t, that is this 1 by 2 t e raised to minus t into 2 minus t. Again 1 by 2 out of the integration sign, and you have to find derivative of this function using derivative of product rule with 3 terms. So this here we have to apply d by dx of u into v into w. U is function t, v is function e raised to minus t, and w is nothing but 2 minus t. Same rule you have to extend for the 3 terms. So applying this rule of differentiation, we get this step. Here you have to take u dash, that is derivative of t is 1, v into w as it is. Then u as it is, derivative of v and w as it is. Then u into v as it is and derivative of w. On simplification, you get these steps. Here in all the terms we are having e raised to minus t common factor. So you can take it outside the curly bracket. You will get the terms containing t or the constant terms inside the curly bracket. Now adding or subtracting the similar terms, we get the final answer as 1 by 2 e raised to minus t into bracket t square minus 4t plus 2 as the final answer. If it would have been s cube upon s plus 1 bracket cube, then in that case you have to take derivative of this function again, so as to get the final answer. Now this is very simple example. Now there are 2 types of examples in this method. Just now we have seen type 1 example. Now second one is somewhat different and it requires some another method as assistant method to get the final answer. So now here you may observe s square upon s square minus 1 bracket square. So here we cannot write this function as s square into 1 upon s square minus 1 bracket square, because if we consider this function as f bar of s, then it is not useful to find inverse LT of this function. So you have to choose some another method to reach the final answer. We will see the solution step by step. Here f bar of s is considered as 1 upon s square minus 1. See, in the given function it is s square minus 1 bracket square, but we are considering f bar of s as 1 upon s square minus 1 only, because its inverse LT can be easily written. So we are going to take f bar of s like this, and also its derivative is minus 2s upon s square minus 1 bracket square. So here we are getting the denominator as in the given function. So here we are going to take help of use of differentiation of f bar of s method. We will see the next step. Now taking inverse LT on both the sides of f bar of s, we get L inverse of f bar of s as L inverse of 1 upon s square minus 1, and this is one of the standard results, or we may say that this is similar to one of the standard results, 1 upon s square minus a square, and the answer is 1 upon a sine hyperbolic at. But here a is equal to 1, so answer is sine ht. So this is our f of t. Now here we are going to use the use of differentiation of f bar of s method in between. So you have to write its corresponding result. But we know that if L inverse of f bar of s is equal to f of t, then L inverse of d by ds of f bar of s is equal to minus t f of t. So using this method you can reach the answer very easily. So using this result we can write L inverse of minus 2s upon s square minus 1 bracket square, that is L inverse of d by ds, and d by ds is minus 2s upon s square minus 1 bracket square, and minus t f of t means minus t into sine ht. So this is our latest result. Still there is one more factor -2, and in the given function it is absent. So you have to use linearity property of inverse LT. So using that property, we can take -2 outside the inverse LT operator. Therefore -2 L inverse of S upon S square minus 1 bracket square is equal to minus T sin HT. On both the sides, -1 is a multiplier which get cancelled, and you can take this 2 on LHS as 1 by 2 on RHS. So this is our latest result, L inverse of S upon S square minus 1 bracket square. Now the given function here splitted as S into S square upon S upon S square minus 1 bracket square. So this was your f bar of S, and you have obtained its inverse LT like this. And now you are going to use the differentiation of f of t method. So using the result L inverse of f bar of S is equal to f of t, then L inverse of S into f bar of S is equal to d by dt of f of t. So now this is your f of t. So we get L inverse of the original function is equal to d by dt of 1 by 2 t sin ht, 1 by 2 out of the differentiation operator. So it is 1 by 2 d by dt of t sin ht. Again here the functions of t are in product form. So you have to apply u into v rule of derivative. U equal to t and v equal to sin ht. Derivative of sin hyperbolic t is cos hyperbolic t only. So using uv rule of differentiation, we get the answer as 1 by 2 into sin ht plus t cos ht, or you can say 1 by 2 sin t plus t cos t. So this is our final answer. So this is the second type of examples where we have applied the use of differentiation of f of t method. So in this way you can solve the examples where s is a multiplier to some function of s. This is also very useful method. Now some examples for practice are given here. Question will be same. First example, s square upon s plus 4 bracket cube. Refer example 1 in this video to solve this example and verify your answer with this given answer. And second one is s square upon s square plus 1 bracket square. Answer is 1 by 2 sin t plus t cos t. Here you have to refer solution of the second example and verify your answer with this given answer. So in this way we have completed 6 methods out of the 7 methods to find inverse Laplace transform of the given function of s. Now in the next video we will discuss how to find inverse Laplace transform of the given function of s using the convolution theorem. Convolution theorem application to find inverse LT is very favorite subtopic of the university question paper setters. So surely there will be at least one example in every question paper, in every university question paper, where you will find the example to find inverse LT using convolution theorem. So after these 6 simple and easily understandable methods, we will discuss the last and important method, use of convolution theorem to find inverse LT, in our next lecture. Till then, make a good practice of these 6 methods. Thank you.